Hi everyone, I'm Sneha Martin, currently pursuing MCA at Marian College Kuttikkanam Autonomous. Today, we are going to dive into a fascinating concept in graph theory, Euler Graphs. Ever wondered how a delivery driver finds the most efficient route or how circuits are designed to avoid unnecessary loops? Euler Graphs hold the key. Let's explore this amazing concept together. Euler graphs revolve around the idea of traveling through every edge of a graph exactly once. This concept dates way back to 1736, thanks to the genius of Leonhard Euler, who first used it to solve a real-world puzzle, the famous Königsberg Bridge problem. More on that soon. But why should we care about Euler graphs in today's world? Because they are the backbone of optimization problems in various fields such as logistics, circuit design, and even garbage collection. To understand Euler graphs, we need to talk about two main key points, the Euler path and the Euler circuit. An Euler path is a journey through a graph that visits every edge exactly once, but we start and end at different points. This happens only if exactly two vertices have an odd degree. An Euler circuit does the same but a tiny difference. It starts and ends at the same vertex. For this to happen, every vertex in the graph must have an even degree. Think of it like drawing a picture without lifting your pen and without retracing any line. Sometimes it is possible and sometimes it's not. Now, I am going to introduce you an Euler's formula specifically for planar graphs. V minus E plus F is equal to 2, where V is the number of vertices and E is the number of edges and F the number of faces in the graph. This formula applies only to planar graphs which can be drawn without edges crossing. It helps us determine the fundamental properties of a graph. Now, let's step into the shoes of an 18th century Königsberg resident, the problem that started it all. The 7 bridges of Königsberg asked whether one could walk through the city and cross each bridge exactly once. Euler analyzed this as a graph problem and found that no such path existed there. Euler proved that it is actually impossible. This is the birth of graph theory. The graph representing the Königsberg had more than 2 vertices with an odd degree. And as we just learned, an Euler path can only exist if at most 2 vertices have an odd degree. This meant that the problem had no solution, an insight that revolutionized mathematics and led to the development of graph theory. So, how do we actually find an Euler path or Euler circuit if one exists? One way is Fleury's algorithm. Imagine you are walking along the edges of a graph. You must make sure that you never cross a bridge that, if removed, would disconnect the graph, unless there is no other choice. By following this rule, you will successfully find an Euler path if that exists. Fleury's algorithm provides us with a step-by-step method to find an Euler path or Euler circuit in a graph. Here is how it works. Start at any vertex or a specific vertex. Second, choose an edge to traverse, avoiding the bridges unless necessary. Third, remove the edges after traversal. Fourth, continue until all edges are covered. This algorithm ensures efficient traversal of Euler graphs in real-world applications. Now let's explore some interesting relationships between Eulerian graphs and other type of graphs. First, we have the bipartite graph. A bipartite graph is Eulerian if and only if it is connected and all vertices have an even degree. Next, we have the regular graphs. A k-regular graph is Eulerian if k is even. Complete graphs. A complete graph Kn is Eulerian only if when n is odd. These relationships help us understand where Euler graphs fit within the larger world of the graph theory. Euler graphs aren't just an abstract mathematical concept. They have real-world applications that impact our daily lives. In waste collection and street cleaning, Euler paths help design efficient routes so trucks don't retrace roads unnecessarily. In logistics and delivery services, companies like Amazon and FedEx optimize routes to ensure every road is covered once, minimizing fuel and time. Network design in electrical circuits and computer networks, Eulerian graphs help ensure efficiency by reducing redundant connections. Despite their usefulness, Eulerian graphs come with limitations. They require strict conditions such as all vertices must have an even degree for a circuit to exist and the graph must be connected. In dynamic or changing networks, Eulerian paths may not always be practical. Additionally, for very large graphs, checking degrees and connectivity can be computationally expensive. But despite these all challenges, Euler graphs remain a fundamental tool in mathematics and optimization. To wrap up, Euler graphs are a powerful concept in graph theory with deep mathematical significance and practical applications. From the Königsberg Bridge problem to modern logistics, their impact is undeniable. By understanding Eulerian paths and circuits, we can solve complex real-world problems efficiently. This is all about the Euler graphs. Thank you for your valuable time and attention.